What's up, everybody? Welcome back to another episode of Modern Hobbyist. In this video, I'm going to show you how I get super smooth time lapses of my resin 3D prints. Let's get started. Welcome back, everybody. I'm Charlie with Modern Hobbyist. If you haven't already, make sure to subscribe and click that bell icon so you get notified every time I upload a new video. Now, if you've been watching my videos or following me on Instagram for a while, then you know just how much I love to get smooth time lapses of my 3D prints. And I don't just mean any old time lapses where I set my camera to time-lapse mode and let it go until the print is done. No, I'm talking about super smooth time lapses like this. I outlined how I'm able to do this in a previous video, but the overall gist is that I use Octoprint and a plugin called Octolapse to pause the print and have my digital camera take a snapshot at appropriate points. This process is only possible because the Raspberry Pi running Octoprint is able to establish a USB connection with my 3D printer, so it knows exactly what line of G-code is executing at any given moment. Anyways, I recently got an Anycubic Photon Mono, so naturally, I immediately tried capturing time lapses of my resin prints the same way I do with my FDM printers. Unfortunately, the Photon Mono doesn't support USB communication, aside from reading files from a USB stick. And on top of that, Octoprint doesn't support resin printers at all. Fortunately, resin printers use UV light to cure the liquid resin at each layer, so if I could find a way to detect that UV light pulse, I could know exactly when each layer is being cured. I also already know how to control my camera with a Raspberry Pi since I had already done that before with Octolapse. So all that was left to do was detect the light pulses. This was as simple as picking up a PhotoResistor module on Amazon and writing a quick script on the Pi to read the signal and trigger my camera when a light pulse is detected. And just like that, this project was done. But I still wasn't happy with it. This solution, although it works, it requires a Raspberry Pi, an SD card, several custom scripts, a few external libraries, and of course, an external power supply. All in all, this solution just had way too much overhead to get up and running, and worst of all, it took way too long to boot up and actually start the script. So with all those issues in mind, I went back to the drawing board and got started working on a better solution. The first problem that I wanted to address was the boot up time. Now, the only reason I chose a Raspberry Pi in the first place was because I already know how to control my camera with one over USB. This time, if I replace the Pi with an Arduino Nano, I can completely eliminate the long boot times and setup overhead, but I also lose the ability to communicate with the camera over USB. Fortunately, my camera can also be triggered from the 2.5mm remote shutter input on the side of the camera. So as long as I can find a way to use that remote shutter, this solution should work. So for version 2, I went with an Arduino Nano and the same light sensor module from before, but this time I had the Arduino send a signal to a 3.5mm headphone jack that would be connected to my camera via a 3.5 to 2.5 adapter cable. But I didn't quite feel comfortable connecting my camera directly to an electrical circuit that was being powered externally. Instead, I used an opto-isolator to isolate my camera's electronics from the Arduino's electronics. If you're not familiar, opto-isolators use an internal LED to light an internal photoresistor, which in turn allows a current to flow through it when the LED is lit. So the camera shutter is connected over one side of the opto-isolator, and the Arduino is used to control the internal LED in the opto-isolator when a UV light pulse is detected. And with that, I now have another working solution to this problem, and as far as my electronics projects go, this is a pretty elegant solution, at least for me. It boots up quickly, it protects my camera from externally powered electronics, and it's fairly simple to put together. But I'm still not happy with it. Again, this solution requires that the Arduino be programmed in the first place, and then the Arduino requires an external power supply to function. To me, this just seems like way too many wires, too many plugins, and an overall messier setup. So one last time, I went back to the drawing board and tried to come up with a better solution. This time, I took a close look at what the opto-isolator was actually doing. To put it simply, when the internal photoresistor inside the opto-isolator saw the LED light up, it allowed the camera's 3.3 volt signal to travel through it. With that in mind, version 3 of this project scrapped the use of microcontrollers altogether, and instead I simply took a photoresistor and connected it to the same 3.5mm jack as before, along with a 10K resistor to prevent the camera from triggering in low light conditions. So after hours of over-engineering and then more hours of un-engineering, I finally have the perfect solution that I probably should have thought of immediately. This simple circuit works entirely off the camera's own 3.3 volt output from the remote shutter jack. So worst case scenario, the camera will just think that I'm constantly holding the shutter button down with my finger. All that's left to do now is do a little soldering and mount it onto my printer. And with that, this project is done. Now if I ever want to take a time lapse of a resin print, I can simply plug a cable into my camera and the jack on the back of the printer, and I'm ready to start the print. If at any point I don't want to create a time lapse of a resin print, I can just unplug the cable from the back of the printer, and all that's left is an inconspicuous little black box that won't affect its normal use at all. The only thing to do now is to see how well this thing actually works. In the end, I couldn't be happier with how simple and effective this project turned out, even though I probably should have thought of the final solution first. But I wanted to show my entire process of solving this problem to show that sometimes the first or even second solution you come up with isn't always the best solution, and more complex doesn't always mean better. In this case, I was able to simplify my solution from a Raspberry Pi all the way down to basically a cable with a photoresistor on the end, which, of course, is already a product you can buy. Unfortunately, after coming to my final solution, I decided to Google it to see if anybody else had come up with anything like this before. And naturally, I did come across a product called ResinLapse. ResinLapse is basically a streamlined version of what I created here, so if you aren't interested in soldering your own, it might be a good investment for you. Anyways, that's all for this video. If you want to give this project a shot, I'll have a link to all the parts and wiring schematics I used, as well as the code for the Raspberry Pi and Arduino if you want to take that route. Leave me a comment below if you have any suggestions or improvements for me to make, and if you liked this video, make sure to smash that like button and subscribe so you don't miss any future videos. On the topic of future videos, this is the last video I'll be recording in this little shop of mine before we pack up everything and move all the way across the country. So you might not hear from me for a while, but that will give you plenty of time to go back and watch all my older videos. Although don't go too far back because some of those older videos are pretty embarrassing. Anyways, that's all for this video. Thanks for watching, and I'll see you guys in the next one.